Video, we're going to introduce the concept of a mathematical function. We're going to discuss some important properties of functions. We're going to then review graphs of linear univariate functions. And that brings me to the point that for most of this video, we are going to be dealing with single variable functions, though in other parts of the course, we will consider multivariate ones. Finally, we're going to introduce the concept of a function inverse in a single dimensional setting. Okay, so what is a function exactly? Well, a function is a mathematical object that assigns each input value to a single output value. And the key here is to remember single output. Basically, if you have a mathematical assignment that assigns an input value to multiple output values, then it is not a function. So the function is characterized by single output assignments. So as a brief example, something like plus or minus the square root of x is not a function. And that is because if x is 1, then the function, or the argument rather, is assigning to the output both plus and minus 1. And obviously plus 1 does not equal minus 1. So some object like this is not a function. On the other hand, an object like f of x equals x squared is going to assign a single output to every input. Now, mind you, x squared, if you have f of 1, is going to equal f of negative 1. But that does not mean that f is not a function, because for both 1 and negative 1, there is still only one output, not two, as in the case of plus or minus square root of x. So that's what we mean by a function assigns each input to a single output. They do not necessarily have to be unique outputs for every input. We will discuss refinements of functions and different types of functions later when we do want to have unique outputs for each single input. So in general, an input or an output need not be a single number. It can also be a vector of several numbers in multidimensional space, just like this object, x1, x2, x3, dot, 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 up to xn, where the dimensionality of this vector is n, little n. What functions do is x passes through the function, and the function is just essentially a set of mathematical instructions that operate on the variable x. And when those instructions are complete, the output of the function y is then returned. So x goes into f does some work inside, performing some algebra, etc., and then outputs y. Okay, so let's consider some unidimensional functions. A unidimensional function, univariate function, or one-dimensional function is just y equals f of x, where y and x are numbers. So they're not vectors, but numbers. So y and x are what we call scalars, or just numbers. Single numbers, not vectors. So in the case of these unidimensional functions, we call x the independent variable, and as I said, it's a number, and y is the dependent variable. So the dependent variable depends on the independent variable. Y depends on x via the operations performed by f. And f is the assignment. It is the function. Not all assignments are functions. All functions are assignments. So I mentioned earlier that a function must output to a single value for every input. Well, a way graphically of testing this in the one-dimensional space is to use what's called the vertical line test. And the vertical line test is a simple way to check if a unidimensional assignment is indeed a function. If you can essentially draw a vertical line through every part of the assignment and pass through only one point at each x, so at each x, then the assignment passes this test and it is a function. Let's consider the unit circle here in figure 1. So the assignment is f of x equals plus minus the square root of the quantity 1 minus x squared. Notice that if I draw a line vertically at any point except the endpoints of the circle, I'm passing through 1, 2 points in the y dimension, and that means that this is not a function. So the expression describing a circle is actually not a function. However, over here on the right-hand side, we have a cubic polynomial. F of x equals x cubed minus 4x squared plus 1/3 x. Anytime I draw a vertical line through this function, I'm passing through only 1 point. And this happens for every x. This is true. So f is passing the vertical line test for every x, and thus f is a function. So some important features and properties of a function are the sets of values that the inputs and the outputs can take without committing a illegal operation like division by zero. So here's some important definitions. The domain is the set of all valid inputs for a function. So if we have f of x equals y, the domain is the set of all x's that f can take legally. While the range is a set of all possible outputs, so it's all possible y's that f will generate for any given x. So some examples. We have a multivariate function. So we have f is taking a vector x1, x2 all the way to xn. And this vector resides in the n-dimensional real number space. Suppose f outputs to the natural numbers, integers, say it rounds every real number to its nearest integer. It's a rounding function. Then this is a function. The domain here, in this case, is going to be Rn. So in this case, this is the domain. And the range is just the set of natural numbers. So there are many functions that can have this feature. Okay, that's what we mentioned. Now we consider the function x squared. So in this case, any x will do. You can square any real number, whether it's negative or positive or zero, and you are not at risk of committing an illegal algebraic operation, such as division by zero. However, whenever you square a number, whether it be negative or positive, you're only ever generating a positive number. So the output is 0 to infinity, and we know that it's bounded below by 0 with close bracket because when you square 0, you get 0 back. So 0 is indeed in the range of the function. Now, the bigger the number you get, or the bigger the number you put into the x position, the larger the output is going to be. And so this is actually unbounded above, and the range is thus 0 to infinity. Finally, considering the function 1 over the quantity x minus 3, what we want to consider here is all possible values x for which a potential illegal operation could occur. So whenever x minus 3 equals 0, we have division by 0. So basically, we do not want x to equal 3. In fact, we can show that we can have any x such that x does not equal 3, and we will be okay and not commit any illegal operations. So that means the domain of this function is negative infinity to 3. We use this cup U symbol to denote a union, and 3 to infinity. So there's essentially a hole in the domain at 3. Further, if we look at the range of this function, note that extremely negative numbers are going to, like negative 1,000,000, are going to lead to values very close to 0, but on the left-hand side. So the negative infinity to 3 part of the function appears to be bounded above at 0. Extremely large numbers on the right, however, are going to induce an extremely large positive number in the denominator. And we know that 1 divided by an extremely large number in magnitude, like say 1,000,000, is going to be very close to 0. So the number is bounded below by 0 when we are in the 3 infinity part of the domain. Now, where do we get the range diverging off to negative infinity, infinity? Well, we need to think about numbers close to 3, but not exactly equal to 3. So, for example, if we're back here on the left and we're considering a number just smaller than 3, so say like 2.999, well, 1 over 2.999 minus 3 is 1 over negative 0.000001, for example. Well, this number is very large in magnitude and actually goes to negative infinity as you get closer and closer to 3 from the left. The same phenomenon occurs as you approach 3 from the right. Say if you have 3.00001 minus 3 is again positive 0.0001, and that is how you diverge off to positive infinity. We'll do some more of these exercises in the discussion session where we take a function and we derive its domain and generate its range from points around or on the domain and try to figure out exactly how the function is diverging off toward infinite values or condensing or asymptoting around other particular ones that are finite. Okay. So having now examined the domain and range of functions, let's take a look at graphs. So you can really only graph three-dimensional functions. You cannot really graph four-dimensional functions because as human beings, we cannot perceive 4 dimensions. We can only perceive visually 3-dimensional functions. Today, we're really only going to consider 2-dimensional functions, so functions that are essentially flat on a piece of paper, for example. So with 2-dimensional functions, we're going to graph functions where we have the coordinates x, y equals f of x. The y-intercept of such a function is going to be the value when x is 0, the value of f when x is 0. And the x-intercepts are what are known as the roots of the function. And these are the values of x that force y to be 0. So a linear function is going to take the form y equals f of x equals mx plus b. M is going to be the slope of the line, which we can find by picking 2 points, say x1, y1, and x2, y2, where y1 is the output of f of x1, and y2 is the output of f of x2, and then we can compute m equals the difference between the y's divided by the difference between the x's. Indeed, we call this rise over run. And that is going to be the change in y divided by the change in x. So this is change in y divided by change in x. So b is the y-intercept also. We call the y-intercept b. Now, considering how to graph this line, if you want to take a moment and pause the video and try to graph this line on your own, noting that the y-intercept is -1, slope rise over 1, run is 1/2, go ahead and do that, and then resume the video when you're ready to work through the problem together. Okay. So we're wanting to graph the line f of x equals 1/2 x minus 1. The first thing I'm going to note is where the y-intercept is. And this is going to give us a good anchoring point on where the line is going to, or on a point on which the line is going to go through. So we have the y-intercept at -1, which we can see down here. This is -1 in the y dimension. We're going to then draw the line by looking at the slope. So from the y-intercept, we're going to rise up 1. And then we're going to run over. So run denotes movement along the horizontal axis. Rise denotes movement along the vertical axis. So we're running over 2 and rising 1. We've now found a new point, and it's the point 2, 0. This gives us our m equals 1/2. So now we connect the original y-intercept with the point that we just drew by exploiting the fact we know the slope is rise over run. We've found 2 points. Having 2 points are sufficient to then draw a line, and we have thus completed our task of drawing the line y equals 1/2 x minus 1. Okay. So continuing, a quadratic function is a function that takes the form f of x equals ax squared plus bx plus c, where these a, b, and c values, these are what are known as coefficients. So these are coefficients, but we also can just know them as essentially numbers. These are numbers for our purposes. So don't get too confused by the letter notation. Don't let the notation get you down. So these are just coefficients, and they can be zero. B and C and A, all of them can be zero, in fact. The graph of a quadratic function is called a parabola. When A is positive, the parabola is going to open up. That means it's going to be a U shape like so. So this is A greater than 0. And when it's negative, it's going to open down. It's going to be like this. It's going to be an upside down U. To find the real roots of a quadratic function, we can factor it, or we can always use the quadratic formula. Only certain functions can actually be factored. The quadratic formula can always be used. And it's x equals negative b plus or minus the square root of the quantity b squared minus 4ac, where this value is known as the discriminant. B squared minus 4ac, that's the discriminant, all divided by 2a. And it's going to be worth memorizing this function. You may need it in many of your courses, and your professors are probably going to expect you to have it memorized. So the vertex of this parabola is the point negative b2a, f of negative b2a. And what we can do is now we can solve these quadratics using either factoring or the quadratic formula for their roots. So these are be solving these for all real values of x. So go ahead and take a moment and solve these quadratics for x by rearranging them. Note that you may have to subtract 3 from both sides here in A, or subtract 1 from both sides in B. Or with C, you could square both sides. So we want to rearrange these. And then after doing so, you can either factor, if possible, or use the quadratic formula. So if you want to take your time solving these, go ahead and do so, and pause the video. Okay. So solving quadratics, let's take a look at A. We have x squared plus 2x equals 3. What we're going to do first is we're going to subtract 3 from both sides and isolate it into canonical form so that we have x squared plus 2x minus 3 equals 0. Once we have x squared plus 2x minus 3 isolated on the left, we can easily factor. And we can factor the left-hand side and note that x plus 3 times x minus 1 equals 0. Factoring is sort of a holistic it's a holistic exercise. It's a holistic analytical pursuit that requires being able to kind of see it before you can do it. Now, if you can't factor, you don't see it necessarily, you can always use the quadratic formula, which in this case we have a equals 1, b equals 2, and c is negative 3, because we're essentially subtracting that to get it in canonical form. Now, in order to use the quadratic formula, remember, we actually need to be able to have the quadratic equation written such that there's a 0 on the right-hand side. If you have a number over here, you need to pull it over and add it or subtract it from C. So if we were to use the quadratic formula here, we would be writing negative 2 plus or minus square root of 2 squared minus 4 times 1 times negative 3 all over 2 times 1. And we can go ahead and compute this. You can see that inside of this radical in the discriminant, we have 4 minus 4 times 1 times negative 3. So minus 4 times negative 3 is 12. So we have 4 plus 12 is 16. So we have minus 2 plus or minus the root of 16 over 2, which is this root of 16 is just 4. So we have minus 2 plus 4 is 2. So we have either 1 or minus 2 minus 4 is negative 6. We have negative 6 divided by 2 is negative 3. Now you're going to see that the answers we got using the quadratic formula here are going to be the same as the answers we're going to get